Hello and welcome to my presentation. Today I'm going to talk about my current project for the EE583 class. Well, the paper I have picked was focusing on the explainability of the AI for the unsupervised learning algorithms and in particular for the K-means algorithm. The explainability of the AI is actually a hot research topic because most of the time for many of the applications that are commonly used today by the framework of the AI, although they give really good decisions most of the time. Generally, the decisions they give are not so much intuitive to a human observer. So we uh, sometimes need uh, sometimes need simpler models that may give the same result and at least give us a really satisfactory explanation. And also, within the framework of the unsupervised learning algorithms, they are generally used for the recommendation algorithms within the either social media applications or I don't know, maybe hotel booking applications, these kind of things. And since these are generally consumer-based applications, these kind of recommendations need some kind of simple explanation to convince the user. So that's why we need the explainability. Uh, but one problem with the explainability is that since we use generally simpler models to get the same or similar at least classification results, generally the results are less accurate compared to more complex models. So there's always a trade-off between the two. But anyway, at least in order to make a good balance between the two, we start with the tree-based approach, which are generally the most explainable type of the AI, and also I will show the steps that will make it more accurate compared to simple trees, decision trees that we know of. Well, the methods I will present the method in two steps, and also the paper authors actually presented them within two different papers. So the first thing is that as you can see in the slide, on the left side of this picture, there's a graph, and this is the result of the K-means algorithm to 2D data, and we have 5 clusters here. And as you can see, generally we have linear-like decision boundaries between two different clusters, and when all of the clusters get their boundaries get really close, we can see these kind of complex shapes. And as the number of features get higher and higher, instead of two, if they're like I don't know, 1,000 or maybe a million, these boundaries get even more complex. So instead, what we want is that seeing some boundaries that are dependent on generally just one single feature, as you can see the X here, for instance, uh, and they're also parallel to the other axes. These are easier to interpret for a human observer. And as I said in the first slide, decision trees can achieve this. What we do at each node of the decision tree is that we pick one sample either randomly or based on some kind of metric, and we compare it to a threshold, and based on this we give a decision until we come to the leave nodes at the end. And as you can see here, for 5 mean centers or 5 clusters, if we limit the tree to have 5 leaves at the end, we get this kind of result. But one problem or one caveat with this approach is that this has, in a way, unacceptable amount of mistakes within it. As you can see, this single dot here should normally belong to the cluster 0, and even by just looking at this, I think we should also decide for the 0 for this thing, or this dot again here belongs to 4 with this decision tree approach, but while it should normally contain within 2. So what we want is that still, based on this tree approach, based on these rectangular decision boundaries that are parallel to the original axis, generating a new method that preserves the explainability but increases the accuracy a little bit more. And how we can achieve this is that instead of defining k number of leaves for a tree, we can pick the number of leaves to a higher number. As you can see, instead of 3, they pick 6 here, and after defining, after growing the tree to its maximum extent, we can assign each of these leaves to one of the original cluster centers here. So this will give us a more accurate approach, as can be seen here. For 3 clusters and 3 leaves in the tree, we can see many mistakes that were done by the tree model here. But if we go to the this picture where 6 tree leaves have been used, now we can see that many of the mistakes were the that should belong to cluster 0 originally still remains in cluster 0. Only fewer mistakes can be observed this time, and even by further increasing this 2k number to something like 3k, 4k, this can be arbitrarily decreased even more, and we can better result. And by the way, of note, instead of a standard decision tree which uses some kind of impurity measures as their metrics, these trees still use K-means metric of alter norms to make their calculations, and this is one of the differences from the general card or classification and regression trees that we know in general. So these are the basics of the algorithm, but to see some of the results, we have to make some comparisons to certain data sets within the for the paper. What they were using within their algorithms were generally some libraries that use scikit-learn for Python, and these are also some for data sets they have used in their results that can be directly called from the scikit as well. So these are some standard data sets that are used either for supervised or unsupervised learning metrics. But for their results, they were comparing 3 algorithms. These were these newly introduced methods. 2 of them were contained under this. One was starting with just a simple empty decision tree, and one was starting with the previous algorithm where the maximum number of leaves were first set as k, and starting from that they apply this new algorithm, and the third algorithm they use is just a card, the general standard decision tree algorithm that everybody knows of. And in order to show the cards may fail in certain circumstances, a specific data set has been designed just for this case, where most of the data is consisting of just ones and zeros, but just 2 of the data, and just one feature within 2 of these data shows some outlier response by having an exceeding large value of 1,000, and we can see the result of this. For the first data sets, what we see here is that these are actual satisfactory results. On the x-axis, we can see the increasing number of leaves, and we can see that the cost is decreasing. And the y-axis shows us the cost ratio. This is the ratio of the cost that is obtained from the algorithms that we can see in this legend, the 3 algorithms, and their cost divided by the cost of the original k-means, which is the baseline algorithm that we try to make the comparison of. So what we wanted is that we already assume that the 3 algorithms gives a really good explainability, but what we want to see here is that if they can give same accuracy results with the original baseline k-means, and just seeing that this ratio gets approaches 1 more and more shows us the better gives us a better result. And for most of data sets, we can see it. Only for maybe this data set, it is a little bit higher than the expectation, but still it converges to the value of 1. And the reason may be that this is a 2D data set of images, a little bit different from the others. But in all of these all the three algorithms show satisfactory results. But when we go to this synthetic data set, we can see that the cost ratio of the card gets a value between 5 and 6, which shows the this time the power of the our new designed algorithm of this one, where it can converge to 1 for both of the cases where we start from an empty tree, and a tree which uses the previous algorithm based on the same thing. And in order to show the performance a little bit better, I have also picked a dataset myself, if independently it can show similar results. Within the dataset, there are 50,000 data, and each of them has 14 features, but only 6 of them were numerical, which I have used here because this will give more reliable results for the clustering. And also the range of the different features were really different from each other. So before putting it into the clustering, so that one will not dominate, I made a mean and max normalization before the classification. And here again, you can see a really nice cost ratio of almost 1 for all of 3 cases. So this is basically what we want. So to sum up, today I presented a new explainable AI algorithm, which gives good accuracy results, but still makes the results of the decisions more intuitive to humans. And we saw that it can achieve this arbitrarily well for different data sets, and we get close accuracy results to baseline k-means. And within the paper, they also say that maybe for some of the machine learning pipelines, for some of the applications, this can even replace the standard k-means, because it's simpler, and calculation-wise, it gives less costs, but this is some future work. So that's where I end the presentation. Thank you.